Okay, so what I just did real quick is just wrote us a summary of what we know so far, that matrix A is our coefficients, matrix X for this next one is just talking about our variables, and B is what it's equal to, so for AX equals B. Alright, now this is what Cramer's rule says. Okay, Cramer's rule that says for any kind of system that you have it in the form of AX equals B, that whenever you want to solve for a variable, so this is going to be in general, I'm not going to do it in the I1s and I2s and all that stuff yet. I'm going to give you general notes, and then we're going to come back and actually solve it for this. Okay, so let's say I want to solve for the first variable, x1. Then what you do is you go into your matrix, and we're going to find the determinant of a manipulated matrix. Okay, remember the parallel lines that you normally think of, oh, that's absolute value. We're talking about a determinant now. So I'm going to show you what A1 here is in a second. But then we're going to divide by the determinant of the matrix as is. Okay? And you're going to do that for every variable. So like if I want to solve for my second variable, it's going to be determinant of a manipulated A coefficient matrix divided by the determinant of the matrix as is. Okay? So basically how you find, let's say, A1, what you're going to do is you're going to replace, since it's A1, we're going to replace the first column of matrix A with our solution matrix, so with B up above. To find A2, we're going to replace, since it's A2, we're going to replace the second column of matrix A with our answer matrix, which is B. Okay, so if we go up there, then what you're going to see is we know already A is the 10, 4, 4, 12. Okay, so what A1 is going to be is in the first column, instead of 10 and 4, we're going to have 6 and 9, and the second column stays as is. What A2 is going to be is the first column then stays the way it is, so 10, 4, and the second column now becomes that 6 and 9. Okay, and so to finish basically solving this out for the rest of Cramer's rule, it says then that x1, whereas our first variable, which in our case is I1, is going to be the determinant of this A1 we just wrote divided by the determinant of A. Okay, I2 is going to equal the determinant of A2, which we just found, over the regular determinant of matrix A as in general. Okay, so again, A above, our regular A, is the 10, 4, and 4, and 12. So let's go about real quick and finding the determinant of basically these three. Remember the determinant, how you find it, so I guess let's write them off to the side. So the determinant of A1 is going to be 6 times 12 minus 9 times 4. The determinant of A2 is 10 times 9, so go along the diagonal from the top left to the bottom right, minus the other diagonal, so 6 times 4. And then the determinant of just matrix A as in general, which we found before, but we can do it again. It's going to be 10 times 12 minus 4 times 4. Okay, so if I put all these into a calculator and get my answer, so 6 times 12 minus 9 times 4 is 36. 10 times 9 minus 4 times 6 is 66. And then this one, just like from before, was 104. Okay, so let's finish out solving for I1 this way. So I1 is the determinant of A1, which is 36, divided by 104. And I2 was the determinant of A2, which is 66, over 104. And if I plug these into my calculator, you're going to get I1 to be 0.3462, and then I2 to be the 0.6346. So either way, we got the same answers that we did before. One way using the whole concept of finding the inverse. So if I had ax equals b, I moved the a over and I solved this way, a inverse times b, and the other way using Cramer's rule, where I manipulated my original matrix, and it's then again all based on determinants. Okay, so let's go on to our second example. Okay, well in this second example, what we're looking at here instead of circuits is we're looking again kind of like at that spring thing. And really what, if I kind of draw on this and kind of show you guys some stuff, it's what's happening is you've got 95, basically a weight that's providing 95 newtons of force down, okay? And then what we have are these two cables at the top providing tension. So we got tension 1 and tension 2. And they're all being kind of, the ropes themselves are being held at certain angles. One's at 45 degrees and one's at 30 degrees, okay? And our goal is eventually to find what T1 and what different tensions do we have. We're going to find them both through matrix algebra and through Cramer's rule, just like exactly what we did in this last example. Okay, and the main equations that we build off is the fact that in order to keep this item just kind of sitting here nice and pretty without shaking to the left and right or without swaying, is we have to get all of the forces that's acting on this system balanced. Okay, and so that's why it says the sum of the forces is going to equal 0. Well, the reason why, let's look at these terms closely. So the tension that's coming from the 45-degree angle, so the tension of the 45-degree angle and the tension of the 30-degree angle has to be 0. So why one's negative and why one's positive, you can almost think about it as if you thought that the center here was 0. Since T1's going off to the left, it's going into the negative x-axis, and T2 is going off to the right, it's going into the positive x-axis. Maybe you can kind of think about it like that. Or just the fact that a negative and positive it's going to help balance it out. But the key with this first equation, it's all about balancing the forces along the x direction, along the horizontal direction. And so really think about T1, since it's on the left, it's going negative. Okay. Now let's go to the second equation. We're summing up the forces in the y direction, and the sum of the forces have to be 0. Okay, so the tension, the vertical tension at 45-degree angles and the vertical tension at 30 degrees needs to be 0. Okay, now the reason why both of these are positive is that, again, if you thought about this center point, pivot point as being the origin, since T1 and T2 are both pulling it up, then that's why they're both positive. Okay, now there's one little change we have to make, is because in order for this really to be kind of quote-unquote balanced to 0, is we have 95 newtons pulling down on this system. So really, to balance it out, this system needs to equal 95, not equal 0. Okay, the 0 in the x's is good because there's not a weight pulling it right or left. What the weight is doing is pulling it down. So we need these almost like the vertical tensions to equal 95, which is the vertical tension pulling it down. Okay, so here are our two main equations. Obviously, if we put the cosine of 45 into our calculators and the cosine of 30 and the sine of 45 and 30 both into our calculators, let's actually get more of a numerical coefficient. And then that way we can see really what we're looking with. Okay? So in that case, then we can almost consider it to be, when I do cosine of 41, it's going to be a negative 0.7071 T1 plus 0.866 T2 equals 0. And then the other time, you're going to get 0.7071 T1 plus a 0.5 T2 equals 0. So here's really our system of equations. And like we did before, let's go ahead and declare our matrices. So matrix A is just the coefficient matrix, which is negative 0.7071, 0.7071, 0.866, and then making sure that's, and then 0.5. Okay. That's matrix A. Matrix X represents our unknowns, which in this case are going to be T1 and T2. And then matrix B represents what we're equaling, which is 0 and then 95. Okay, so basically built off of these three matrices right here, then we can, 1, solve this using the matrix algebra, and then 2, by Cramer's rule. So coming down just a little bit more, let's do, here's the matrix algebra. Okay, matrix algebra basically says that if I'm going to solve it, then x is equal to A inverse times B, where specifically A inverse is 1 over the determinant of matrix A times the, oops, I was about to say D and I wrote B, but I need D. So I'm going to swap D and A and then switch the signs on B and C. Okay, so that's how we're going to get the inverse. Let's go ahead and find it. So A inverse is going to be 1 over the determinant of A. And remember, I guess let me write this part too, just so we can kind of recap. The determinant of A is AD minus BC. Okay, so AD, it's going to be pretty big, but negative 0.7071 times 0.5 minus B times C, so 0.866 times 0.7071. Okay, so that's 1 over the determinant, and then swapping some around, we're going to have 0.5 now on the top left. This bottom one's now going to become negative. The top right's now going to become negative. And that bottom right is now swapped, so 0.7071. Okay, so we have 1 over all of that mess times then this matrix. So if you want to get that matrix in our calculator, or if you get the matrix in your calculator and then divide everything through by that, or you can tell your calculator to say, hey, let's multiply this matrix C by 1 over this, and then it's going to come out with a brand new matrix. So let me go ahead and just do the math for you, and y'all, if you want, definitely get practice by plugging this in your calculator. Make sure you get this your same way, but it'd be negative 0.5177, 0.7321, 0.8966, and 0.7321. Okay, running out of room here, but we got a matrix right there. Okay, so going back, our answer then is going to be this inverse matrix, so negative 0.5177, 0.7321, 0.8966, and 0.7321, and we multiply that. I'm just going right here telling me what to do, times our B, and our B is 0 and 95. Okay, and when we do that and plug that on our calculators will tell us that T1 is going to equal 85.2, and I guess I can put some variables or some units in here. It's going to be newtons because it's tensions, okay, of force, and then T2 is equal to 69.5 newtons. Okay, so I know I'm kind of all over the board with this, but let's kind of just recap real quick. Anytime you do the matrix algebra, it's just your inverse matrix times B. Okay, and how to get your inverse matrix? It's 1 over the determinant times some terms swapped around in your matrix. So 1 over the determinant times your new kind of swapped around matrix A, and then going back and multiplying that new thing times your B, and then you're done. Okay, so let's use this whole exact same thing and let's do the Cramer's rule instead and see if we get the same answer.